Hello, this is Joshua and welcome back to our lecture. So for this video, we will be talking about the solvent for your biochemical reactions, and then again the topic outline is provided on the following slide. So these are the specific topics that we'll be covering for this video. Okay, so you just have to go through there, and then note that small emphasis will only be given on topics number 3 and 4, as this will be discussed in your Anachem class. So we'll only be focusing on its importance and application in biochemistry. Okay, so for this slide, let's answer the question, what makes water polar? Okay, so remember that you have different types of bonds, no? So one of which is your covalent bond. No? It's the sharing of electrons, okay, between two atoms to form a bond. And under covalent bond, okay, so you have here your nonpolar covalent bond. No? So okay, this is a type of bond when there is equal sharing of electrons. So kailan ito nangyayari? When two or more atoms of the same electronegativity, okay, forms a bond. So remember that electronegativity is the ability of an atom in a molecule to attract electron or to pull electron towards itself. And then the other type is your polar covalent bond, no, na present sa ating water molecule. So this is a type of bond present when there is an equal sharing of electron, okay, or of electrons, no, as a consequence of difference in electronegativity, okay, thereby causing your molecule to have a dipole moment. No, so meaning there is a presence of partial charges. No, so partial negative yung side kung saan nandoon yung pinaka-electronegative na atom, kasi nga sabi natin hinahatak niya yung electron papunta sa kanya, and then partial positive naman doon sa inalisan or naalisan ng electrons. Okay, so this slide shows you electronegativity. So remember, we've already discussed electronegativity on the previous slide. Okay, so note that there are molecules that have polar bonds present but are non-polar molecules. No, you call this your overall polarity. So, kailan ito nangyayari? Yung sinabi nga natin na merong polar bonds but are a non-polar molecule. Okay, so here you have to take into consideration yung kanilang geometry. Okay, so ang iniisip ko dito, for example, in your carbon dioxide, since same oxygen atom, yung bonded sa either side ng carbon, okay, nagka-cancel out yung pag-pull ng electron sa left side and then sa right side. Again, since they have the same electronegativity. Okay, so let us note that the polar nature of water largely determines its solvent properties. So for example, ionic compounds are usually strong electrolytes. So meaning they undergo 100% dissociation or ionization, or that they tend to dissolve in water. Also, okay, polar molecules with partial charges tend to dissolve in water. Remember, the two substances that have the same intermolecular forces are likely to be soluble with each other. No? So you have to remember here, like dissolves like. No? So the underlying principle here is your electrostatic attraction. Okay, so for ionic compounds, no, the interaction between ionic compounds with water. Okay. Also here you have your ion dipole interaction, no, example of which is your KCl dissolved in water. Okay. You also have here your dipole-dipole interaction, which is present when you dissolve ethanol or acetone in water. No? So these there are actually examples for these, no, on the following slides. Okay, so this is what happens when you dissolve ionic compounds in water. No? So you form here your hydration shells. No? So your ionic compounds get hydrated by water. No? So how does this happen? The partially positive side of your water molecule surrounds, okay, the negative atoms, whereas your partial negative side surrounds the positive atom, rendering your compound dissolved, no, in water. Remember that opposite charges attract. Okay. Okay, now next, okay, You have na here ion dipole and dipole-dipole interaction. So these type of interaction help ionic and polar compounds dissolve in water. No? So the take home here is that opposite charges attract. Okay, so your water molecule will position itself such that it will make available its side that has the positive charge to that of the compound you're trying to dissolve. Okay, so still with the solvent properties of water, no? So when we say hydrophilic, we're referring to a substance that is said to be water-loving, no? So meaning they tend to dissolve in water. Whereas when we say hydrophobic, we're referring to a substance that is said to be water-feeling, no? Which tends to not dissolve in water. And then when we say naman amphipathic, no, think here your SDS, your sodium dodecyl sulfate. So these are molecules that contain one or more hydrophobic and one or more hydrophobic regions in the same molecule. Okay, so shown here is an example of the structure of your amphipathic molecules. Note that it has both polar, okay, and non-polar character. So note also that the interaction between your non-polar molecules is very weak. You call that your van der Waals interaction. So again, you have your polar head, okay, and your non-polar tail. So remember this because this is very important in the formation of your lipid monolayer, your lipid bilayer, micelle, etc. Okay, so what is micelle formation? So this is achieved when you have amphipathic molecules, as mentioned on the previous slide. So that, okay, so this is achieved, so that their hydrophobic parts are buried inside the sphere, as shown in the figure, and their hydrophilic parts are on the surface of the sphere, and in contact with the water environment, as shown in the figures. So this is the mechanism of how you clean greasy stuff. Okay, so you have to surround your dirt with your micelle before you can wash it off. Okay, so now we move to hydrogen bonding. So hydrogen bond is a partial interaction between a lone pair, okay, on an electron-rich donor atom. So this type of bond usually occurs when the positive end of one dipole is hydrogen atom bonded to an atom, okay, of high electronegativity. So most commonly your oxygen or nitrogen and sometimes your fluorine. Okay, and then the negative end, okay, of the other dipole is an atom with a lone pair of electrons. Most commonly, okay, your oxygen or nitrogen, and again sometimes your fluorine. So as a shortcut, you can just remember HK, just want to have fun. F-O-N. So this type of interaction is very important, especially in stabilizing the three-dimensional structure, okay, of your biological molecules, such as that of your proteins, your RNA, and most importantly, your DNA. Okay, so note that H bonding is a non-covalent bond, and is considered as a special case of dipole-dipole interaction. So why is hydrogen bonding important, and how does it work? Okay. So when hydrogen bond is covalently bonded to your F, O, and N, okay, the partial positive charge that occurs in your hydrogen atom can interact with another electronegative atom, so specifically your FO and N. Now, all of your three atoms, okay, as shown on the left side of the picture, all lie, okay, in a straight line, which forms a hydrogen bond. So now, that arrangement actually allows for the greatest possible partial positive charge, okay, on your hydrogen atom, and consequently the strongest possible interaction, okay, with the unshared pair of electrons on the second electronegative atom. Okay, so remember, we've made mention earlier that H bond is not a covalent bond. It's just a special case of dipole-dipole interaction. Note, however, that although it is weaker than your covalent bonds, they have significant effect on the physical properties of hydrogen-bonded compounds. So remember, you've studied this in your org chem class. So this is actually one of the particular reason, okay, why we have such stable genetic repository. Okay, so now we move to acid, bases, and pH. So let's just recap the basic definition of your acids and bases. So remember that your acid is a molecule that behaves as a proton donor, and that your base is a molecule that behaves as a proton acceptor. So you also have to remember here the different definitions, okay, of your acids and bases. Okay, so remember, di ba, you have your Arrhenius, okay, your Bronsted, and Lewis definitions. Okay, so now we move to acid strength and pH. So one can actually derive a numerical value for the strength of an acid, or the amount of hydrogen ion released when a given amount of acid is dissolved in water. Okay, so acid strength is described by your KL value. Again, it tells you the extent of the dissociation of your acid to its component ion, in effect giving you how much proton is dissociated in your system. Okay, so here, you need to be able to recall your knowledge in your chemical equilibrium, and how to write your K expression. Remember also that your pH is a measure of acidity of your solution. Again, your pH is a measure of acidity of your solution. It's simply the negative logarithm to the base 10 of the concentration of your hydronium ion. So we will not be deriving this here. Let us also note that most bodily fluids, most body fluids have pH value in the range of 6.5 to 8.0. So we often refer to as your physical pH. Okay, so your Henderson-Hasselbalch equation is used to connect your Ka to the pH of solution containing both acid and base. So by using this, you can actually calculate the ratio of your weak acid, HA, to its conjugate base, A negative, as provided in this slide. So basically, you can use this when you're dealing with buffers. So from that same equation, we see that when the concentration of your weak acid and conjugate base are equal, okay, the pH of the solution equals the pKa of the weak acid. Why? Because the logarithm of 1 is 0. Okay, so by the way, to get pKa, you just have to get the negative logarithm of your Ka. Also, we see that when pH is less than your pKa, okay, your weak acid predominates, while when pH is greater than the pKa, okay, the conjugate base predominates. Okay, so now we move to buffers. So remember, this is just a review of your analytical chemistry. Okay. Buffers are a solution whose pH resists change upon addition of small to moderate amounts of strong acid or base. So note that the composition of your buffers are a weak acid, K, and the salt of its conjugate base. So provided here are some examples of your buffers. So remember, also have to remember here the concept of your buffering capacity, so which is related to the concentrations of your weak acid and conjugate base. So the higher their concentrations, okay, the higher the buffering capacity. So now we move to the importance of buffer. So what's the importance nga ba of buffers, especially in biological system? Okay. So because the importance is this, since biochemical processes are sensitive to small changes in pH. So that's why we need to control and monitor pH, especially when we're conducting biochemical experiments. And one way of doing that is knowing your buffers. That being said, okay, the buffer system is the primary, okay, protection of organisms to harmful pH changes. So remember that your enzymes, okay, actually have optimum pH, to where they work best. And sudden changes in pH, sudden change in pH can actually lead to protein denaturation. Okay, so let us note that the intracellular pH of most cells are actually maintained by your phosphate buffer system, no? In the range K between 6.9 and 7.4. While the important buffer system in your blood is the bicarbonate carbonic acid couple. Okay, so some trivia. Did you know that hyperventilation causes increase in your blood pH? Why? Because when the volume of air breathed into and out of the lungs increases above what is normal, more carbon dioxide is exhaled. Now, new equilibrium is established between your bicarbonate ion and carbon dioxide, no? Causing respiratory alkalosis. And then vice versa naman. When you undergo hypoventilation, okay, mag-decrease naman ang iyong blood pH, no? Also known as your respiratory acidosis. Now, lastly, no, listed here, no, are the following criteria when you're selecting a buffer. Okay, so how do you select a good buffer, especially when you're studying biochemical processes? Okay, so your buffer system should reflect both the need for pKa, okay, so for your pKa value, your pH 7, and its compatibility with the metabolic machinery of the cell. So you can just go through the list, and that's it for this video. Thank you for listening.